In the first three chapters of this DVD, we're going to lay some groundwork. I'm going to set some foundation and explain some basic principles that'll help you understand as we go along. The first chapter is about what HLSL is. It's important to understand what the shading language is before we start learning it. In the second chapter, I'm going to talk about the graphics pipeline and how data flows from one end of the graphics processor chip to the other. And in the process of that, I'm going to explain where the vertex and pixel shaders fit into that pipeline and how you can program those vertex and pixel shaders. Finally, in Chapter 3, I'm going to be talking about the setup that we'll use as we write shaders. So before we get into the specifics of HLSL, it's important to understand what it is. HLSL stands for High Level Shading Language. It was created as a collaboration between NVIDIA and Microsoft to make it easier to create programs for the graphics processor. Now, some of the first computer programming languages were written in code that's called assembly language. And what that means is it's instructions that tell specific parts of the computer hardware exactly what to do. So here we're looking at a program called Effects Composer that I'm going to get into a little bit more detail on in Chapter 3. And here on the right side of Effects Composer, I have an example of a program written in assembly language. And you can see that it's just extremely cryptic. You can learn how to write programs this way, but it's quite a bit more difficult. So just like the first computer programs were written in assembly and then more high-level languages like C were developed after, HLSL was developed to take shader writing out of the assembly language area and move it into something that's a little bit more clear and easy for artists and programmers to create. So the first thing that you'll notice is that HLSL is based on C syntax. So we have function calls, and it's quite a bit easier to read and understand than the assembly language. What's nice about HLSL being based on C syntax is that it makes it really easy for programmers who've already learned how to program in C or C++ to jump right in and start writing shaders right away. Now, for artists who haven't used C or C++ before, it's still pretty easy. It's not quite as complex. It's not even as close as complex as C or C++ is. And so it's at a level where an artist who hasn't done any programming before can learn a few simple programming concepts and then jump in and start writing shaders. And that's what we're going to do on this DVD. I'm going to explain the programming concepts. By the time we're done, you'll be able to write some shaders. So I think it's important to understand the difference between real-time shaders and shaders written for offline rendering, for example, for a mental ray or a Brazil render or something like that. For real-time shaders, the highest priority is speed. Since these shaders have to be rendered at over 30 frames per second, a lot of other things have to be sacrificed in order to achieve the required speed. For example, all offline rendered materials in Max will use all the lights in the scene. The more lights you add to the scene, the slower it'll render, but it doesn't matter how many lights you add. They'll all be used automatically because that's how the renderer is set up. Just to illustrate that, I'm going to switch over here to Max, and you'll see I have a simple teapot here with the standard material assigned to it. And I've got a couple of Omni lights here in the scene, and I can hit render, and you see that, obviously the teapot's using all the lights I've got. Now if I go over here to lights and just add a couple of more Omni lights, just throw some more Omni lights down there into my scene, you can see that, the render is automatically using all the Omni lights that I've added to my scene. If I look here in my scene selection, I've got 6 Omnis, and they're all being used in the renderer. And that's no big deal for an offline renderer, because it can just take as long as it wants to, basically, to do the math. The goal with an offline renderer is convenience and also image quality, whereas the highest priority with a shader, a real-time shader, is the real-time speed. So let's switch over here to an example of a real-time shader that I've made, and we'll apply that shader to my teapot. I just have a simple brick texture here. And what you'll notice here in this control panel, and I'll talk more about these settings in an upcoming chapter, what you'll notice in this control panel is that I've got specific light slots. And in these drop downs, I can pick which Omni light in my scene I want to fill that slot. But what you'll see is that there are only 3. And what that means is that this shader is being rendered real time in the viewport, but it's only actually using 3 of the Omni lights in my scene. And the reason for that is each Omni light has to be specifically programmed into the shader so that the shader knows exactly what it's going to be doing, which lights it's going to be using. So that's one example of something that's less convenient in an HLSL shader, and so we're sacrificing that convenience for speed. It would be possible to create a shader in HLSL that would use a variable number of lights, but the additional code required for that would make the shader run slower, and every light you added would also make the shader run slower, so HLSL shaders trade convenience for rendering speed. Another example is textures. When you're using a standard Max material or most other offline material in Max, the objects render just fine whether or not you have textures in the slot. For example, let's assign our standard material to our teapot again. And you'll see under maps here that I've got no maps assigned at all. And yet, when we render the teapot, it still shows up just fine with the lighting. However, if we jump over here to our real-time shader again, and we assign the real-time shader to the teapot, and let's say we have our diffuse texture applied here, the brick texture, but let's get rid of that just by dragging none up to that slot, and you'll notice that the teapot is now rendering black. Well, that's because there's no code in the HLSL shader to handle a case where there is no diffuse texture. And the reason for that is it would be possible to write an HLSL shader that said, if this slot is empty, then, proceed without it. However, that if statement would make the shader run slower. And since the whole idea of a real-time shader is fast rendering speed, we sacrifice the convenience of that feature for speed. So that's just 2 examples of features that are present in standard Max materials that don't work right in HLSL shaders, and the reason for that is because HLSL shaders have to run as fast as possible. So based on this understanding, you can probably see that when using HLSL to write shaders, it's best to write lots of short, efficient shaders that each do a very specific job. For example, if you have an object that doesn't need specular highlights, you should write a shader that doesn't do specular at all, instead of just leaving that map slot blank, for example. So it's better to write short, specific shaders than to write one big uber shader that does everything. Uber shaders are fine for offline rendering where convenience is more important than speed. But for HLSL shaders, fast is the whole point. So anything that slows it down has to be removed. And just for one final comparison, if we look here at our options, we can see that we've got ambient and diffuse color and some specular settings, and then a normal map slot, but that's about it for this shader. And if we switch over to the standard Max material, they've got texture maps here for everything. So if we were going to write a shader like this in HLSL, we'd probably write one more specifically geared to exactly what the object we were working on needed, instead of having a material that just had all the possibilities. Anyway, so that's a little bit of an explanation of the difference between HLSL shaders and regular offline rendering materials. And the main difference is just in the priority. With offline materials for regular rendering, the priority is on image quality and user convenience, whereas with real-time shaders, the priority is on speed. In the next chapter, we're going to cover the graphics pipeline. That is how the data flows through the graphics chip. And I'm going to talk about how vertex and pixel shaders fit into that graphics pipeline, and how the shaders that you program in HLSL will be run on the graphics chip.